And this is the class you've all been waiting for, the class where we're going to look at the definition of a derivative, the central concept of calculus. Now, of course, you have looked at this definition before, you have seen it in high school, but as all kinds of other topics that we're visiting in this course, even though you may have seen it before, right now we expect you to really understand it deeply. So it's not just a matter of going through this definition and say, whoo, thank goodness we can forget it eventually, but we want to make sure that you understand it and are able to use it at any time. So some of the things I'm going to show you will look familiar, and that's okay, but make sure that they not only look familiar, they look yours. So we're starting from a function y equals f of x as usual. We're going to pick a point on this on this function by picking an x coordinate c and constructing the corresponding point c comma f of c. So the x coordinate is c, the y coordinate is f of c. Then what we do is we move a little distance away, which traditionally is called h, and we're going to pick another point nearby at some x coordinate c plus h and corresponding y coordinate f of c plus h. Once we've done all this, we can identify the slope of the secant line. That's the line that cuts through the curve at those 2 points. And computing the slope of a line that goes through 2 given points is very easy. So it's given by the rise over run, and of course in this situation the rise is the difference between the y coordinates, so f of c plus h minus f of c, and the run is just the difference that we moved horizontally, and so that's just h. So we're going to indicate this for now with this rather cumbersome notation: m for slope, sec for secant of c, meaning that we're starting at the point of x coordinate c, moving a distance of h. Okay, so again, that notation of course will disappear soon, but keep in mind that all of this depends on both c and h. Now, this can be interpreted as the average rate of change of the function. It tells us on average how much has the function changed, or how fast has the function changed as it moved from c to c plus h. We can play this game, in fact, for any point that is near c. As long as my h is not 0, because of course if I end up with a 0, I have a 0 in the denominator, and that's a problem. So for instance, I can move that point a little bit closer to c. I can move it even closer if I want to. I can even go to the other side. All I have to do is pick an h that is negative. So I can play this game for every value of h except 0. I cannot compute it once again for h equals 0, because I end up with an indeterminate form with a 0 in the denominator. And in fact, if our function is continuous, the top will be 0 as well, right? F of c plus h, when h becomes 0, will become just f of c. All right, but that is really a very interesting situation that we're missing, because that's what will give us the tangent line. So, right, if we think of a tangent line, that'll be sort of a secant line with the 2 points coinciding with each other. But now that we've worked with limits for a while, we know that when we have a situation where we have a function, namely that slope, that can be computed for every value of h except 0, we're going to use limits. So let's see how that is done. So what we're going to do is we're going to start from that formula, the secant formula, the slope of the secant line, and what we're going to do is we're going to arrive at the slope of the tangent line by taking the limit as h approaches 0 of that slope formula, rise over run. So I'm not going to read it, you can read it on your own. Okay. Notice that this is never a boring limit, right? Because there is always an h in the denominator that makes it interesting, and in fact, in most interesting cases, there will be a 0 on top as well. So it will be a 0 over 0, and we've seen that that is something that sometimes can be worked out to be a number. Okay. Also notice that this slope can be viewed as the instantaneous rate of change of the function at c. How fast is the function changing at that particular instant, or at that particular point? So that is what the derivative is going to tell us, and we're going to tell a little bit more about it in a minute.